This is part 2 of the Linear Regression series. In this video, we will cover the overfitting and regularization. This video was produced in Korean and translated into English. My voice was generated using AI text-to-speech. In the last video, we looked at the basics of ordinary least squares. In this video, we will look at the LASSO and Ridge regularization methods to prevent overfitting. And we will implement the linear regression using the optimization class from scipy library. Overfitting occurs when the regression line fits the training data so well that it does not fit the test data, which is new or unexperienced data. In the example below, the blue dots are training data and the red dots are test data. The blue line is the regression line fit to the training data. This describes the training data very well, but not the test data well. The error for this test data point is large. The red line is the regularized regression line fit to the training data. The regularized regression line slightly reduces performance on the training data, but improves performance on new data. This is the effect of regularization. On the other hand, underfitting occurs when the regression line is too simple to describe both the training and test data well. If the regression line is too simple like this, the errors in both training and test data increase. Regularization is a key technique that prevents overfitting by adding a penalty term to the model's loss function. If the mean squared error loss function looks like this, add the regularization term here. When minimizing this loss function, the first term serves to reduce the loss, and the regularization term prevents the loss from reducing excessively. In the example on the left, applying regularization has the effect of slightly decreasing the slope and slightly increasing the intercept. Regularization prevents the regression line from being too sensitive to x and produces a slightly flatter line. Next, let's look at the LASSO and Ridge regularization methods. The multivariate regression line looks like this. There are k features x and k parameters w. And there is b, which is the bias or intercept. Let's write this equation as follows. If x0 is 1 and w0 is b, these two equations are equivalent. Then we can simply write it as follows. And let's consider a constrained optimization problem with one constraint. We have an objective function like this, and we want to set a constraint such that the sum of the squares of w cannot be greater than a certain value c. These constrained optimization problems can be solved using Lagrangian methods. Using lambda, a Lagrangian multiplier, we can write the constrained objective function as follows. This is a function of w and lambda. Since lambda is a variable, its optimal value must be determined. The optimal solution can be obtained by differentiating this equation with respect to w and lambda respectively and solving the simultaneous equations. However, in our problem, we cannot set the upper bound c manually. Instead, assume the lambda is a constant. Then, lambda c also becomes a constant, and the following equation can be obtained. Here the lambda is a regularization constant and a hyperparameter. This is L2 regularization, the ridge. By setting the constraint like this, we can get the equation above. This is L1 regularization, the LASSO. If both of these conditions are used as constraints, both terms can be added to the loss function. This is called the elastic net regularization. Now let's look at the effect of regularization graphically. There are parameters W1 and W2, and the loss function looks like this. This location is where the loss function is minimal. At this location, let's say W1 and W2 are 7 and 6 respectively. When regularization is applied, the optimal solution will be at this location. Let's say W1 and W2 at this location are 3 and 5.5. Applying regularization makes W smaller like this. On the other hand, loss increases slightly. These parameters may better describe the test data. The loss increases slightly, which may degrade the performance on the training data slightly. The source of this figure is this site. This time, we will compare the effects of LASSO and Ridge. Ridge uses the sum of W squares, so we can think of it as the equation of a circle. There are W1 and W2 axes like this. And this location is where the original loss function is minimum. And these are contour lines. The further inward you go, the smaller the loss. Due to the constraint, the feasible region is limited to this area. Then, this location where it meets the contour line becomes the optimal solution. Loss increased slightly and W1 and W2 decreased. In the second figure, the optimal solution is at this location. In the third figure, it is at this location. In the case of LASSO, because the absolute value of W is used, the feasible region is diamond-shaped. In the first figure, the optimal solution is at this location, and in the second figure, the optimal solution is at this location. And in the third and fourth, the optimal points are at the vertex. In the third and fourth figures, W2 is 0. In LASSO, contour lines are more likely to meet vertices. So certain features are more likely to be 0. In other words, LASSO has the effect of selecting specific features. The source of this figure is also this site. Now let's implement linear regression. Let's try a numerical method using scipy's optimization class. Apply ridge regularization. Create the data we will use like this. Set up a regression line and randomly generate the data points mixed with Gaussian noise. Set the slope A and the intercept B to 0.5 and 0.3 respectively, and randomly generate 1,000 pieces of data. The standard deviation of Gaussian noise is 0.2. The generated X and Y are like this, and we will use this equation from the previous page. Add a column vector x0 of all ones. Then, the equation of the regression line can be simply written as follows. The regularization constant is set to 0.01, and the regularized loss function, using mean squared error, is defined like this. The error is set to y hat minus y. Add a regularization term to the mean squared error. The ridge method is used here, and save the history of W and loss for later use. Now we perform the optimization process. Minimize the regularized loss function defined on the left using scipy's optimize.minimize function. The first argument is a loss function. The second argument is the initial value of the parameters W and W1 to be optimized. W0 is the intercept and W1 is the slope. If args is true, the function on the left stores the history of W and loss. The variable result contains the optimal solutions, W0 star and W1 star. Now let's visually check the training data and the predicted regression line. Display the training data X and Y like this, and draw the Y hat predicted above. The regression line is expected to look like this. Result.x variable contains the optimal parameters. Multiply this by the feature x values to get y hat. Next, let's visually check the loss function and the path to the optimal solution. Let's draw the change in loss when W0 and W1 change in this three-dimensional space. Set the W0 and W1 values using the mesh grid function. Create a grid like this with values from -5 to +5. Then we calculate all the loss values for W0 and W1 values. Then the loss for each point will be these locations. Use these values to draw a 3D loss function. And visually check the path to the optimal point. The trace W list updated in the function on the left looks like this. The first column vector is the history of the intercept. And the second column is the history of the slope. And the third column is the history of the loss. In the first iteration round, when W0 and W1 are equal to this, the loss will be this value. In the second iteration, when W0 and W1 are equal to this, the loss is this value. As the iteration progresses, the loss will gradually decrease. And W0 and W1 will converge to the optimal solution. Let's draw the history of these values. And finally, check the R-squared score. First, let's use the formula we saw in the previous video. Then let's use scikit-learn's R2 score function and compare the two results. The optimization result is as follows. Successfully converged to the optimal solution. The optimal solutions are like this. And the R-squared calculated with this formula is this value, and the one calculated with the R2 score function is also this value. The two results are exactly the same. And the generated training data looks like this. Training data was extracted from this model. The actual A and B are 0.5 and 0.3 respectively. The predicted regression line is like this. The predicted slope, A, is 0.509 and the predicted intercept, B, is 0.295. This matches well with the actual values. Next, let's visually check the loss function and the path to the optimal point. There are W0 and W1 axes, and the z-axis is the loss value. The loss function is a convex function like this, and you can see that it starts from here and goes well to the optimal solution. The coordinates of the starting point are set to 4 and -4. This is the starting point. To get a clear view of the route, I used a point a little further away from the optimal point. Now let's run this code. -4 and +4 were used as initial values for W0 and W1. The result came out like this. It was successfully converged to the optimal solution, and the estimated parameters are as follows. The training data and the regularized regression line are like this, and the loss function and the path are observed like this. And R² is observed like this. So far, we have looked at the Ridge and LASSO regularization methods and implemented them in code. In the next video, we will look at the mean centering and data normalization and analyze the Boston house price dataset. Let's use the scipy library, like in this video, and compare with the results from scikit-learn's Linear Regression, Ridge, LASSO library.